Okay. Good morning, everybody. I would like to start by make a brief recap of what we have seen last topic we have seen yesterday, which is the separation of the stress energy tensor of any operator, indeed, into a local equilibrium part plus a correction. This is a separation which relies on the choice of some hypersurface at the present time, where this is the one at the which defines the statistical operator, which we have called local equilibrium time zero. This is supposedly the best approximation of the actual density operator. And so, if we want to calculate something at point x, we have to choose this hypersurface, which defines local equilibrium at this hypersurface. Okay, and this allows us to make to separate the mean value of any operator into two parts. So the first part is the value at the local equilibrium with this operator, rho LE, which is written like e to the minus the sigma mu t mu beta nu divided by z, and the correction. Maybe let me show you again an equation of yesterday, if I found it. So this correction depends on, well, maybe I can show the equation without writing them again. Let's do. So, where was it? Yeah. So we have seen that we can split the integral defining the local equilibrium density operator at sigma naught, which is, as I told you, supposedly the best approximation to the actual density operator, into two parts. So this is the local equilibrium at the time defined by the point x, where we want to calculate the mean value of this operator. And then we have the integral over the region omega. So we have this achieved this decomposition. And then, by using linear response theory, we can calculate the mean value of T mu nu, in the approximation of, I don't know what's going on. Well, okay, that's vanished. Fantastic. So we have T mu nu, the mean value is equal to the approximation of linear response theory to the local equilibrium value plus a correction. Okay, this equation, of course, is general. It means that if we were able to carry on this expansion to the infinite order, and if the series converged, which is another big problem, okay, then we would be able to calculate delta T mu nu exactly. And so, in this way, obtain the exact theoretical value of T mu nu. Okay, but of course, this is practically impossible, so that in the in this field, what we can do is that you can show that you can usually stop at the first order and obtain the so-called Navier-Stokes approximation of stress energy tensor. So where we have T mu nu equals local equilibrium plus a term depending on the gradient. Nevertheless, what I pointed out yesterday is that also T mu nu local equilibrium can be expanded in turn. Okay, because, so if you remember, what we have, I didn't write it on the slides, but you may have taken notes, that we can expand beta nu around the point x here in a Taylor series. So we may write something like d sigma mu T mu nu beta nu. So if you want to calculate this, which would be, by definition, this is T mu nu local equilibrium at the point x. So what we can do, we can expand beta nu around x in a Taylor series, and the first order obtain this formula as we e to the beta x dot 4 momenta plus 1/2 the thermal vorticity times the angular momentum at the point x plus 1/2, and then we had, if you remember, I defined the thermal shear tensor, multiply this operator qx, which is obtained by taking the symmetric combination of x and t. Sorry, this is not in the slides. I will certainly write something here just to and make it available to you. Okay, so this is again a series I mean, this can be continued, of course. This is in a series. You can stop at the first order in the gradients, which means stopping at the linear order in the gradients means retaining just these three terms, and expand again with the linear response theory. So by using this very technique here, you can expand and obtain that T mu nu local equilibrium is equal to T mu nu. Then we have seen yesterday that this would be the first term with e to the minus beta x dot p. What you have seen yesterday's tutor session. This is the ideal term, which means this is of the form rho plus p u with everything depending on x, because this depends on beta x. This can be written like this, plus something, okay? Because now you have this term, they are the so-called B term here. They can be considered as small terms, correct in the expression of the stress energy tensor. They can continue and write something which depends linearly on the gradients of beta, and then you can go on and obtain quadratic terms in the gradients of beta. You can also continue this expansion here in the exponent and obtain second order derivatives of beta with associated operators. Then this means that you also may have corrections of the second order in the gradients and so on and so forth. Okay? And all of them, as you will see in the second part of this lecture, are all of them are non-dissipative corrections, means they do not generate entropy. This is just something which may sound surprising to you, or at least or maybe unexpected, in a sense that this means that the local equilibrium value of stress energy tensor is not given just by this expression, which is the ideal form, the so-called ideal perfect fluid form, but it has something else. Okay? These are usually corrections whose origin is quantum, so they can only be found in a quantum statistical mechanics theory, and they are usually very small, but they can be there. Okay? And for instance, it has been, well, it can be there that this is a rather unexplored field. It has been calculated that at the global equilibrium, there are certainly quadratic corrections in thermal vorticity. So this means that here you have something of the order of omega squared. Okay? And with several combinations, so this has been calculated explicitly for free fields, but also, I mean, there are the expectation that they should be there dates back to, I think, to 2008, in one of the papers that was mentioned by Mike Strickland. Okay? Okay, so hope everything is clear so far. Okay, now the question is, let me, since we have I have mentioned the stress energy tensor, which is important for hydrodynamics, although what you have seen here applies to any operator. So you may, for instance, want to calculate a current, or you may want to calculate something, and we will see this in the last lecture, you may want to calculate something like this. You may want to calculate the mean number of particles in a quantum field theory at local equilibrium. Just because I want to know what is the spectrum of particles, in a relativistic fluid. So you can apply this technique to any operator you want, okay, and separate it into a local equilibrium term. Sorry, this is the, okay, so this is the original one, yes. And so you can expand this in a linear response theory, and you can get a local equilibrium term, a correction, which is this of dissipative origin, and as I told you, I will explain why. I call this correction dissipative. And that's it, okay? Now, let me focus a little on the relativistic hydrodynamics problem, which is one of the motivations of these lectures. Yeah, please.
So if I understand correctly, you have these two, I think there's two power countings involved here, because you mentioned that local equilibrium has quantum corrections.
Yeah.
And then you have non-equilibrium corrections that go
yeah.
different power counting. So do you have something, so there are two independent power countings, no?
Well, I don't know what power counting in terms of gradients you mean.
Yes, because usually a semi-cross
Yeah.
even in terms of H bar.
Yeah. No, I mean, that is, yeah, it would take us some time to show that this is a quantum correction. So, but otherwise, let me just rephrase what your point. So the point of your colleague is that you may have so you have different expansions here. You have an expansion of T mu nu local equilibrium in gradients. That's right, because this is what I have just erased, unfortunately. And you have also you have an expansion of ingredients of this delta T mu nu, okay, which is let me call it, and then you will understand why I promise dissipative correction. So, in fact, there are two gradients expansions which are involved in this business. Yeah. So the one which is concerned with the local equilibrium term, and the one which is concerned with the non-local equilibrium term. Okay. This is correct, and they both have in both appears an arbitrary number of gradients. Okay, and also any derivative, any order derivative, yeah, derivative of any order. Okay, that is correct. So there is no principal difference between these two in terms of gradients. So is there something depending on, say, on quadratic or cubic or quartic or say a higher order derivative? No, there is no principal difference, except there is a very important conceptual difference. Maybe this I can tell you now, which is the following. In these corrections here, you will always find, if you try to expand them, integrals over the whole space-time region. This means that these corrections, in this expansion in gradients, you will have something dynamical, because you will have an integration over the whole space-time region from the initial state to the final state. Okay, or from the initial hypersurface to the final hypersurface. Whereas, in the expansion of this local equilibrium term, you will always have integrals over the present time hypersurface. And these corrections are therefore not dynamical, okay? Because you don't have any combination of 2 points. So in other words, the stress energy tensor here in the expansion of this term will appear with 2 points on the same hypersurface. Whereas in this integral, as you can see, you have a point x, which is at the present time, and you have a point y, which is at any time between the initial time and the present time. Okay? And therefore, this is dynamical. So this is the important conceptual difference. Okay. Yeah.
The quantum H-bar connection is proportional to the power of the gradient.
Okay, for as far as the
There is some reason.
yeah, there is as far as the expansion of the stress energy tensor. Yeah, there is a one-to-one correspondence between h bar and the number of thermal vorticity appearing in the expansion at global equilibrium. At local equilibrium, you may also have symmetric combinations, and this is well, I don't want to tell you something that will be disproved in the future. So let me say, I don't know. Okay, but I think so. So this is my expectation. Yes.
When you have this term in X, and then you are doing this type of integrals over the whole space.
Yeah.
If you are integrating outside the light cone region of X in the past, then could this bring some problems with causality?
Well, no, I mean, I think that this will vanish if it is outside the light cone. Okay, but for those who are educated in this field, this formula here is the first step towards the so-called Kubo formula, which involves the Fourier transform of the commutator of T and T, right? This requires some elaboration, okay? So one has to go through some steps, make some further assumptions about the nature of this region and so on and so forth. But eventually this leads to a commutator of T and T, Fourier transformed, and with some suitable limit. And yeah, what you're pointing out is that since there is a commutator between fields involved, then outside the light cone this should vanish. Yeah. That means that, in other words, that when you calculate this, that is the region which gives non-vanishing contribution eventually. Although in this case you have a correlator, still here you have a correlator, you don't have a commutator. Therefore, okay, this is not principle. This is not. You may have something. I think even outside the light cone at this stage, already, but well, I mean, I have to think about it. Anyway, after some elaboration here, you get really the Kubo formula for what? For something which multiplies the gradients of the velocity and the velocity, the accelerations, and the gradients of the temperature. Therefore, this formula includes, for the present, 3 coefficients. So this formula can be split eventually once you have assumed, approximated this A with global equilibrium and so on and so forth. You can split this into 3 independent coefficients, which are thermal conductivity, viscosity, and shear viscosity. Okay? This is in a sense still folded. So I have not really expanded the whole calculation to show that this includes 3 separate coefficients. Okay? This is really a derivation at the first step, with further steps still to be worked out. Okay, I don't know if I answered your question. No. Okay, so after having cleared this, now let me briefly address the problem of hydrodynamics. So, in this formalism, let me emphasize, this is a quantum statistical formalism, or a quantum field theory, say, problem in which we have some initial configuration, which is described by some density operator, and then we have a final state. Therefore, here, there is no, strictly speaking, it's not hydrodynamics. This is more general. This is a problem of, say, finding some final mean value once you know something at the beginning. Therefore, it is a mechanical, or in this case, statistical, because the initial state is not pure. Okay? So this is a quantum statistical problem. Why is this useful for hydrodynamics? Well, first of all, as some of you asked yesterday, this decomposition is possible, or is a good approximation. So it is an expansion which is viable only if we are in a situation where the gradients are small, as I pointed out yesterday. Therefore, this naturally applies to hydrodynamics, because hydrodynamics is really the theory where you require the gradients, okay, the distance over which these fields, beta and temperature vary, are much larger than the microscopic interaction length. Okay? If you wish, this can be taken as a definition of hydrodynamics. So, a situation where you have a slowly varying macroscopic fields, and you have slowly varying means that they are much larger than the microscopic interaction length. Okay? This is a place where you can split, therefore, the any operator into two parts. Okay? Therefore, it is quite obvious at this stage to wonder what is the relation between this approach and the say, traditional say, hydrodynamics that you have seen, that I have talked about at the beginning of this course. Well, first of all, what is the velocity field in this approach? Well, the velocity field here can be the most natural velocity field that you can take in this framework is this definition. So use beta as a definition of for velocity. Beta is a time-like vector. Therefore, you just normalize it and take this as a for velocity. However, it should be observed that beta depends on what? So beta is not, so you would say, okay, this is quite an objective statement. So I think U equal beta over beta squared. Now, beta is defined as something that I can calculate, right? But when you calculate beta, this indeed depends on the hypersurface. So it depends, you can write this dependence as in two ways. So it depends on sigma or n, except at the very beginning, because the hypersurface is given. But otherwise, when you go at some point x in the future, you have to choose some sigma, which is, after all, arbitrary, in order to define what is local equilibrium. So local equilibrium indeed relies on the choice of some hypersurface. And so when you what does it mean? It means that you have to choose some field n, which is normal to this hypersurface. And therefore, when you solve your constraint mu nu t mu nu equal n mu t mu nu local equilibrium, which is something that you calculate depends on beta. Let me put n here, depends on the metric tensor, okay, like this, in a functional way. So assume that you can calculate this. Then this is an equation which has beta as a solution. But beta will depend on n, because this will depend on the hypersurface, okay? Because I have chosen, after all, a hypersurface in order to write this equation, okay? You see, this equation, it manifestly depends on n. So it manifestly depends on the choice of a hypersurface. I remind you that this equation physically means that we are equating the energy density, the actual energy density, and the actual momentum density to those calculated at local equilibrium. So this is just a constraint we use in the maximization of entropy, okay? Well, so this is a solution which depends on n, and therefore this means that the for velocity will depend on the choice of the hypersurface, which means that we have not really found some objective, in a sense, frame. So it is still the choice of a forward velocity, which is to a large extent, is arbitrary. Okay? Although, I would say in this quantum statistical approach, this is the most natural. It is more natural than, for instance, choosing the Landau frame. The Landau frame is chosen, I think that Mike Strickland has mentioned this, as U, the eigenvector, U is chosen as being the eigenvector of T mu nu, time-like. There is a theorem due to Singe in the 30s, stating that T mu nu, under some very general assumptions, has one time-like vector with a positive eigenvalue. Okay, so this is the Landau frame. Okay, so in this framework, this choice of U is more natural than this. There are also strong motivations, for instance, at global equilibrium. At global equilibrium, it can be shown, for instance, that beta, if you really achieve global equilibrium, means that beta becomes a Killing vector. And at global equilibrium, what happens is that beta is a Killing vector. Therefore, it is a very important vector in general relativity. So being a Killing vector means something, okay? Killing vector, whereas, which is not an eigenvalue of T mu nu, okay? For instance, in a rotating fluid, which is a global equilibrium, it is found that beta is a Killing vector. Of course, you have a vector defined in global equilibrium, but this is not an eigenvalue of T mu nu. So the T mu nu beta nu is not proportional to lambda beta mu. And this means this is something, okay? Means that the Landau frame may imply some problem if say, if you are in situations where, for instance, you have a global angular momentum, which is, so if you have vorticity and so on, okay? Okay, but let me put this aside. Now, the problem is the following. From the hydrodynamic point of view, once you have defined, in a sense, a family of hypersurfaces for each point x, in principle, you can obtain the field beta and therefore solve the problem just by solving this equation. Plus, of course, the one involving the charge current. So, in fact, they are two, or an arbitrary number, because I should also solve this at the same time. So these are 5 equations which have beta and zeta as a solution, and okay, that is, if I solve these constraints, then I'll be able to obtain, solve the problem. But of course, the solution of this problem is, you can say that it is impossible to achieve in practice. Why? Because maybe if you are smart enough, or if you can calculate explicitly an exact solution for this problem. So I'm giving you, so I can give this operator to you, okay? And then, after some very clever calculation, you can solve the problem and find out that and obtain the full dependence of T mu nu onto the involved fields in here, which are beta, zeta that I have not written. Okay, let me also add this, and the metric tensor, which is understood in this problem. Okay, so you can calculate everything and obtain this, the right-hand side of the equation, as a function of some beta. But then what you don't know, of course, in hydrodynamics, is the actual value of T mu nu. this is not known. This is what you want to obtain. Therefore, this is not a dynamical equation, because it won't allow you to calculate beta as a function of time. This is just, it is called a constraint, right? So this is a constraint of your dynamical equation, but this is not a dynamical equation, simply because you don't know T mu nu, okay? So the actual dynamical equation is the following. The actual dynamical equation is when you replace T mu nu with this expansion. This is your actual, the exact expression of T mu nu, and therefore, what you get by equating this to that n mu delta T mu nu should be equal 0. Well, this is a dynamical equation. It is a dynamical equation because delta T mu nu is the correction that I have shown here. So it is this correction, this is just at the first order, but I can continue. And this is also functional of beta and delta beta, and then of course you have gradients. So functional is enough equals 0. Okay? So this is the dynamical equation because this dependence, okay, has derivatives to all orders. So this becomes a partial differential equation. It becomes a partial differential equation which in principle can lead to the solution. Okay? Also, it is very important to point out that although it depends on n, on the choice of a hypersurface. However, there is another approach which would be the most say, obvious in a relativistic hydro, traditional approach. Instead of solving this equation, we can take advantage of the usual, of what is required at the very beginning, that we have seen many times, that the gradient, so that the continuity equation of T mu nu, which is written in this form, okay, which applies because rho LE does not depend on x, because this is just a density operator at some given time. So this can be taken in, we brought in this equation, and then we have 0. So in other words, the mu T mu nu is equal 0. Okay? What is not 0, and please take note, is this one. If I calculate the mu T mu nu local equilibrium x, okay, naively you would expect that this is 0 as well, but this is not, because this depends on time. This is at the time defined by x, okay? This depends on time. Therefore, here you have two derivatives. This means that this is trace the mu rho LE T T mu nu, which is different from 0. Because rho local equilibrium at the present time, of course, depends on the present time, therefore depends on the gradients. Okay? So this is different from 0. So if you use this, this means the mu T mu nu local equilibrium plus delta T mu nu x equals 0. Okay? And therefore, what you do is what you would also make in the classical, so in the traditional approach. Just write down all expanding gradients, T mu nu, expanding gradients delta T mu nu, and write a partial differential equation. Okay? As I've mentioned several times, of course, this is impossible to achieve at all orders. Therefore, you have to stop the gradient expansion at some order. And so the dynamical equations will be truncated at some order in the gradients. If you stop the first order, what you get is Navier-Stokes equations. Okay? You have seen in Mike Strickland's course that this truncation have a remarkable problem, and in that it leads to non-hyperbolic equations. So it leads to some equation which is not causal, relativistic. But it has been pointed out recently, as I mentioned in the first lecture, that this depends on the choice of a frame. So it is possible to achieve first order relativistic hydrodynamics equations without the introduction of, say, a dynamical viscous correction, so without introducing the Israel-Stewart theory in some particular frame, if the coefficients, transport coefficient, fulfill some relation. So this non-causality seems not to be a fundamental problem of this truncation, but seems to be a problem related to the choice of the frame. Okay, and in this field there is an ongoing work which is very intense. Although I'm not an expert, I have to mention that. Okay. Now, yeah, yes, please. Sorry?
So rho, the density matrix for local equilibrium. So shouldn't it should depend on different
Yeah, exactly. So
when you're calculating, while you're calculating with rho is 0, rho L is 0.
rho L is 0 means that this is the initial state.
But if I want to have a dependence of say T mu nu x everywhere, I should use rho L at that point.
No, well, so here, rho L E 0 means that this is the initial state, right? That means that this is the density operator which best approximates the actual one. Okay, so as I mentioned, that we choose some hypersurface where we believe that local thermodynamical equilibrium is achieved, and this is our density operator. And that's it, okay? So this is our best approximation. Now the point is how to express this, and to express this, we use the Gauss theorem, right? So maybe I should write, okay, maybe I can write this down. So we have rho LE 0 is equal to the exponential. And then we have our integral over the initial hypersurface, right? Okay? And this is normalized, of course, in order for the trace to be 1. And this is the density, the density operator at some hypersurface sigma naught. Okay? Now you use the theorem here, this one. Okay? And therefore, what you have is this is equal to the exponent of z minus this sigma at some sigma t, which is an arbitrary hypersurface at some, which whose purpose is to intercept some point x where I want to calculate something in the future. Oops, sorry for my sloppy writing. Where is it? Okay, here, sorry. Plus, and then you have this integral. Okay, so now I have plugged this in, okay, so that is my rho LE0, and it is made of, it has two terms in the exponent, and then what I do is I use the linear response theory, okay, to expand the operator into two parts, okay, therefore this becomes rho LE0 equal approximately rho LET. Okay, now let me translate this. Okay, times, can copy that. Times, now I have to translate everything. It is 1 minus the expectation value of B. What is B? B is this operator here. Let me take it as shorthand. This is B. 1 minus B at local equilibrium time t. Plus, then, okay, I have this. Okay, let me also define A just to, this is A. Okay, so this means that you can approximate for the purpose of calculating mean values, and provided that some, of course, this is a good approximation, say that B is small compared to A, you can expand this local equilibrium, which is your actual density operator, even if it is not the actual density operator, because the actual density operator, as I mentioned, would be the two nuclei colliding. The state of two nuclei colliding, which you don't really know, I mean, which does not lead you anywhere because you don't know how to then calculate the complicated dynamics of QCD. Therefore, this local equilibrium density operator at time 0, which is built on this hypersurface of this Bjorken model hyperbola, this is the best thing you can do for the present to approximate a plasma which is a local equilibrium, okay, at some point. And then you use this. But then you use this expansion in order to, to simplify your calculations, because eventually, what is, after all, the purpose of this expansion? The purpose of the expansion is to calculate the data. So the main focus eventually is to calculate something like this. This is what you want to do, and connect to the previous dynamics. Okay. Did I answer the question? Or?
You were saying that rho LE0 is when we know that hyperbola.
Yeah.
That we know. But for
that we know, that we assume, yeah, of course. Yeah.
rho T, the rho LT you were calculating, that is going to be another arbitrary hypersurface.
Yes, it's an arbitrary hypersurface at some arbitrary future time.
That should be more difficult to calculate, right? Because we don't know what is hypersurface.
No, this is your choice. For instance, you could, for instance, choose the hyperplane and include, put it in there and make a calculation. But it would be easier, okay, in a sense. Easier than calculating over hyperbola. Or you may choose a family of hyperbolae at different times. That is what you can do. In heavy ion collisions, for instance, there is one privileged hypersurface, which is the freeze-out hypersurface. Okay? In a sense, there is. Yeah. Let me draw this. Again, so this is your initial time hyperbola, okay? Or you may choose, there might be some reason why this is not a hyperbola or something more, say, less, say, perfect from a geometrical point of view. Some bumpy hypersurface, I don't know, something different. However, then you have this freeze-out hypersurface, which is usually defined by a condition of, I don't know, fixed energy density or fixed temperature, whatever. To describe the plasma, then what you can do is that you can choose at different times different hypersurfaces like this. Okay, you can connect smoothly to this if you wish. Okay, this is in in general relativity. This is called a foliation of space-time. So a family of hypersurfaces which connect the initial hypersurface to the final one. It's called a foliation. Well, actually, this is not really, strictly speaking, it's not a foliation because it's not made of space-like hypersurfaces, because the final one is not space-like. It has a part which is time-like. However, you can extend the meaning of foliation to also to the time-like case. Okay. So this was just to mention that this hydro problem can be rephrased in this formalism in a suitable way, and well, of course, it has the same, say, degree of arbitrariness that the usual, say, familiar way of presenting this topic has, namely the choice of a frame. So what is the four-velocity field? In this case, there is an obvious, there is a more natural choice of having u as beta over square root of beta squared, which becomes, I would say, objective only at global equilibrium. Global equilibrium because you have independence of the hypersurface. Therefore, that becomes an objective defined field. But otherwise, you have this problem, and okay, that it's okay. The family of this foliation can be chosen as well, and you can write so the hydrodynamic problems in different frames, in a sense, the same way as you do it in the classical approach. Okay, classical between quotes. Okay. There is an important point to be emphasized, and then I think I'm very late on the schedule, on my schedule. That eventually, if we were able, so let's look at this decomposition here that I have mentioned this morning. So we have a separation between the local equilibrium at present time, then we have a correction. Both of these guys depend on sigma, so on the foliation. So they depend on the hypersurface because the very notion of local equilibrium does it, okay? As we have seen, this depends on sigma or n. Depends on which hypersurface I choose at point x. However, the sum of these two will not. So this will not depend on n. Okay? Will not depend on n simply because, well, this was defined as trace rho Le. So this is the actual value. Okay? This depends on the initial state, but the initial state depends on the initial hypersurface, which is a data. It's not a choice, so it's not. Therefore, this does not depend. In other words, the choice of a hypersurface make the separation between local and dissipative and non-dissipative to some extent has a degree of arbitrariness. Okay? Because this will depend on n. But their sum will not. So in other words, this choice, this foliation appears to be, as I mentioned yesterday, a sort of, if you, loosely speaking, I mean, if you allow me to introduce this analogy, a sort of renormalization scale. So it's a sort of, tool which is useful to separate to calculate something, but eventually the final result should not depend on it. Of course, only if we were able to carry on this calculation to the last order. Yeah? And therefore, in this case, then I will lose the dependence on sigma. But otherwise, if I truncate it, I will keep it. Okay? And there it is most likely, it is very similar to the problem of renormalization. Okay? They have a scale which eventually that everything should be independent of it, but if you truncate at some fixed order, you have an actual dependence on it. So you change the scale and your result will change. Okay? Okay, I think that I can stop here, and I have a 10 minutes break, okay? And resume at 11. The second part of this today's lecture is devoted to entropy. Okay. So how is entropy defined? So in quantum relativistic theory, we have seen that entropy is minus the trace of the density operator. Which density operator? First of all, the question is not trivial, because if I take the density operator either in the Heisenberg or the Schrödinger picture, doesn't matter, the result is that S is guess what? What? Right, correct. The result is that S is time independent, so it's constant. So we have this simple equation. Does it mean that anything is reversible? Any process in physics is reversible? Well, perhaps it is. This now points to a very highly debated, and still unsettled issue in modern physics. So what is the meaning of entropy? So is that, or the second law in particular. So does it really mean that there is something microscopically irreversible or not? This debate is a sort of eternal question. Well, I mean, I hope that you understand that ds equal dt is equal 0 because rho is fixed in the Heisenberg picture, therefore it cannot change. But also, in Schrödinger picture, it evolves unitarily, and which then leads to the fact that this is also a zero, derivative 0, even if you take it in Heisenberg picture, the Heisenberg or the Schrödinger doesn't matter. So, for our purposes, then, what is the good definition of, so what is entropy? So we want something which is not constant, because we want to classify, processes as dissipative when entropy increases, or non-dissipative or reversible when entropy is constant, so does not change. So how to, define entropy in a proper way? Well, the proper way of defining entropy is just to tell you the solution. I will try to justify it. That is to take the definition of entropy as the trace of the local equilibrium at any time times the logarithm of the rho local equilibrium at any time. Why? The reason is the following. Rho local equilibrium has been obtained by maximizing entropy with some constraint. Okay? Therefore, what we do here is that we just replace S with S max T. So we replace the entropy with, I would say, primarily defined entropy with an entropy which relates to the fact that we are dealing with a problem of a system which is close to local thermodynamic equilibrium. And therefore, since we have maximized it, it makes sense to start to replace the S with S maximal time T. Okay? This, of course, in principle, can be different from 0. Because this is, as I wrote in one of the last equations, this is something which is, of course, different from 0. Okay? The function of time. Okay. Now, if we accept this, then we can work it out, right? Because now we have S. Now let me take S simply without writing max T. This was just the first step to distinguish between these two definitions. But let me now call it S in a more general way. This is minus trace, then I have rho LE, and then I have, let me see, I can write down, write down again, 1 over Z LE, then I have exponent minus J mu, okay? Then I have trace rho LE, and then I have the logarithm of this density operator. The logarithm of the density operator is equal to minus log Z LE, and then I have the logarithm of the exponent, even if it is an operator, is the exponent, that is easy, plus, minus again, d sigma mu, t mu nu, beta nu, okay, plus, okay, minus j mu, okay. So let me go back now, and we have S equal log Z LE plus the sigma mu T mu nu local equilibrium beta nu minus Z J mu local equilibrium, okay? Well, what I have done here, I have simply taken advantage of the fact that I have to calculate rho local equilibrium with the T mu nu, which is just the mean value of T mu nu at local equilibrium, okay? So this is done over the hypersurface defined by, which is arbitrary, which defines local equilibrium. Now, this could also be written like this, if you remember the constraint that we have used. That this is T mu nu beta nu minus Z zeta J mu. Okay? Why? Because in this sigma mu T mu nu means this sigma mu T mu nu local equilibrium can be expanded in this sigma n mu, okay? Because this is the integration vector, infinitesimal is parallel to the normal vector, okay? T mu nu local equilibrium. And we have seen that this is equal to n mu T mu nu in our definition of local equilibrium. So we can replace this with the actual T mu nu. Now, it's interesting. This formula shows that there are two terms here. One is logarithm of ZLE, and the one is an integral of something. Okay? Now, the question that I want to answer is which appears to be quite natural. Is it possible to write logarithm of? Is it possible to write the logarithm of ZLE as an integral of some potential, or some vector current, phi mu? This problem can be rephrased as, is the logarithm of ZLE in general an extensive quantity? It means can be written as an integral over of the hypersurface, of the same hypersurface, of a vector field? And the answer is yes. And in order to show this, I will sketch a proof of this. Okay, so this is possible. So it's no longer a question. And the proof can be sketched as follows. We take, just a moment. Okay, so we define another operator which depends on lambda, which is defined like this, is e to the minus lambda d sigma mu t mu nu beta nu minus zeta j mu. Okay? Now, z lambda is equal to the trace, by definition, of this operator. And I can take the derivative of log z with respect to lambda for lambda equal 1. This is equal to one z lambda times. Then, okay, we have to take the trace of the derivative of a trace of an operator. Then there are some steps involved. Maybe they can be shown in the last say, tutor session. Okay, how to take the derivative of a trace of an operator, which, in few words, boils down to take the derivative as it was, say, an ordinary real function. Okay, this is just because you have a trace here. Yeah? So when you have a trace, then this makes things very much easier than so dealing with derivation of operators. This is then minus d sigma mu. Then we have t mu nu lambda calculated with this local operator depending on lambda minus beta nu, minus zeta j mu local operator lambda. Now what we do is the following. This is, we integrate again in lambda. Oh, well, from lambda 0 to 1 on both sides. And we have, this is logarithm of z1. So logarithm of z. Logarithm of z at 0.1, lambda equal 1 means this is logarithm of z, because when lambda is equal 1, then of course you get the local equilibrium operator itself. So at the time you wish, okay, so the actual one, and minus logarithm of z lambda naught is equal to the integral of between lambda 0 and lambda of this expression. Put it here. So let me call this f lambda. Okay. Good. Now, assume that we can find lambda naught such that log z of lambda 0 is equal to 0. Example. There is an example. If lambda is infinite. If lambda is infinite, so if we take this infinite, this operator reduces to the projection onto the vacuum. So if the vacuum is unique, so lambda infinite means that you have In other words, if you look at how this is composed, if lambda is infinite, this is equivalent to having temperature 0, okay? Therefore, right? Therefore, because you have e to the minus, if you think about the Hamiltonian, e to the minus h over t, okay? So if you have a parameter multiplying, or perhaps e to the minus beta h, this is more familiar. If you take beta to, if you send beta to infinity, which means t to 0, then the density operator reduces to the projection onto the vacuum. If the vacuum is unique, okay, then logarithm of z, so z must be 1, and logarithm of z must be 0. So if you are able to find a point like this, it means that if you have a theory with a unique vacuum, okay, then the conclusion is that the logarithm of, well, I have to, well, maybe go to the other side.
Sorry, one question.
Yeah.
What exactly is f of lambda?
What exactly?
F of lambda.
Oh, this one. Yeah, this function here.
Okay, but what happened then in the next line with 1 over 0 lambda?
Sorry?
Left-hand side, there is 1 over 0 lambda. Right-hand side. In the first line, there is 1 over 0 lambda. There is 1 over 0.
Oh, yeah, sorry. No, that is, should not be here. Yeah, should be like this. Because this was included in the mean value of t mu nu. I made a mistake. Yeah, sorry. Yeah. So you have just this equation. Yeah. So one of z lambda was my, at the beginning I was trying to make the derivative of the logarithm, but then I realized that this is, yeah, you are right, that this 1 over z lambda is included in this expectation value. Yeah. Okay, so now what we have is the following, is that logarithm, so if such a point, if such a lambda 0 exists, then you have log z equal to integral 1, between lambda naught and 1, d lambda, and then we have d sigma mu, and then we have t mu nu local equilibrium beta nu minus lambda minus minus zeta j mu local equilibrium, which is a function of lambda. Well, now the theorem, the proof is already there. You just need to assume that these functions are regular enough in order to exchange the integration. Okay? So you can write something like this. And here it is. Here we are. So if you take this as definition of phi mu, well, it's done. Okay? So if we are in a situation where you have a unique vacuum, which is, well, in the standard model, this is not really, so, you know, in electroweak theory, this does not happen, but in QCD, well, let's assume that this happens, okay? Or maybe you are in another theory, which is an effective model of QCD, okay, an effective model of anything else. Then you have that logarithm of z can be written as d sigma mu phi mu. So this, let me call it thermodynamic potential current, because this is a current associated to the thermodynamic potential, exists, and I have a formula for that. Okay? Good. That means that under very general requirements, the logarithm of the partition function is extensive indeed. And so what I can write is that the entropy, the way that I have defined it before, is equal to an integral of 3 terms, phi mu plus t mu nu beta nu minus z j mu. Good? Well, does this formula tell you anything? What would be the next step then? What? Yeah, you don't know, but you know, if you see something like this, then the entropy is given by an integral of some hypersurface of 3 terms. Okay. What would be the conclusion? The conclusion is the following: is that an entropy current exists. I can define an entropy current. So I can define a field like this, which defines an entropy current. So it means that I can obtain the entropy by integrating over some hypersurface. Okay? And the S mu is equal to phi mu plus T mu nu beta nu minus Zj mu. So I have obtained a formula for the entropy current at local thermodynamic equilibrium. Okay? And I have derived it. There are subtle or less subtle questions to be discussed about this, but let's take this result as, you know, a solid one for the present. Sorry? Yes, please.
What's phi mu at the hydro level? Because it looks like the hydro formula.
Yeah, what is phi mu at the hydro level? You have to make this integral to answer this question. Of course, I can tell you that this depends, okay, on what T mu nu is in some so a local equilibrium is in some circumstances. Okay, the answer to this question for a particular case will be dealt with in the tutor session of Friday, but let me tell you the result in advance. Phi mu equal P beta mu. Okay? At least, this is strictly speaking, this is an exact result at global equilibrium, at homogeneous global equilibrium. It means the equilibrium that you have seen described by this density operator. So this is an exact result. Pressure, it means that this is the space-space component of a stress energy tensor. Beta mu, then we'll see what beta mu is now, okay? Now we have a formula. And this will be the result of an exercise that you will be seeing on Friday afternoon. If I remember, it's Friday afternoon, right? Andrea, is it Friday? Is it? Andrea, so is it Friday afternoon? Yeah, okay. So not today, but on Friday afternoon. Sorry, I have to wait. You have to wait. But if you want to ask in advance, please feel free to do it. Yeah. Okay, that is very nice. And now we can multiply the entropy current. So now we have an entropy current. Okay, you know what it means? It means that we can calculate the entropy density in any frame. Okay. By just multiplying by some velocity vector, okay? So we have phi mu. Okay, phi mu is, in this case, it's the pressure times beta mu, but this is a special case. In general, you will have to solve this problem. And of course, how to solve this problem? Well, you will have to calculate T mu nu, okay? For instance, you may calculate T mu nu a different kind of local equilibrium or global equilibrium with rotation, etc., and then make this integral. And once you do this, you get this what is the right form of the entropy current. Okay. Now, phi mu plus T mu nu beta nu minus J mu, zeta, sorry, J mu. Okay. Well, I can now use. I can then project this equation onto some velocity vector. So I can take a velocity vector, I can contract with S mu and obtain what should be called a proper entropy density, right? What should I pick up? Well, in this case, with this formula here, there is one special choice of u, which is by far the best. Which one? Yes? Exactly, the one defined by beta. So if I choose u mu equal beta mu divided by square root of beta squared, what do I get? Well, I get the following. I get S, because this is just by definition of contraction with S mu with u mu, okay, equal phi dot u, the scalar product, plus, and here comes the important point, plus what? Plus, I can write this as square root of beta squared, and then I have T mu nu, U mu, U nu, okay? What I have done here, I just took out the amplitude or the magnitude of this vector, which is square root of beta squared, and then I have T mu nu, U mu, U nu. What is T mu nu, U mu, U nu? What's the physical meaning of it? An energy density, right? This is an energy density. Let me call it rho. Well, even if I used rho for the density operator, but this should not lead to any confusion because rho is a scalar quantity and rho is with a hat is an density operator. I may call it epsilon or rho, whatever, okay? I'm used to call it rho, so that if I write equations without thinking too much, I use rho. And then we have minus zeta, and then I have j dot u. What is j dot u? J dot u has the meaning of a charge density, or particle number density, n. Very good. Now, what I want is that this equation reproduce my good old knowledge of thermodynamics, okay? And I should thank your fellow colleague, yeah, in order to, because he pointed out what is the meaning of phi. Phi, okay, assume that phi is equal, this is an exact result of the global equilibrium, as I said, but assume that this is also fine an out of equilibrium situation. Okay, so this would be pressure times square root of beta squared, right? Because this is a P square root of beta squared. So eventually I have the following. I have S equal square root of beta squared pressure plus rho times square root of beta squared minus zeta n. Okay. If I look at that, then I can finally find what is the physical meaning of beta. Physical meaning of beta, well, I could have done this, with other means, but in this course here, the physical meaning of beta now pops up just in the second hour of the third lecture, because now if I compare this with my, well, good old Ts plus mu n equal rho plus p, which was the first equation, that thermodynamic equation that I used in order to work out relativistic hydro, then I can say, okay, this must be 1 over t, right? And this must be zeta, okay, this must be mu over t. And so I have finally found what is zeta, what is the physical meaning of the Lagrange multiplier. This is mu over t, and square root of beta squared is 1 over t. And then I have recovered the thermodynamic relation, which was used to derive which is, I would say, heavily used. Yes, please. Okay. Yeah, where these corrections may of course arise, okay, and they're related to the physical meaning of phi, for instance. Although what you can say is that this is a new definition of pressure, if you wish. What is important to point out, but in principle, yes, I mean you can take this equation, okay? Calculate phi in a more, by including quantum corrections to local equilibrium and find out quantum corrections to the entropy current, which in turn will generate quantum corrections to these relations. Yeah. Okay? But my main message is the following. This equation is not an assumption. It can be derived, okay? So within a quantum framework, then you can obtain a relation between the entropy density, the energy density, the pressure, and the chemical potential, which is, a result. It's no longer an assumption, so it's no longer a postulate, okay? And this, yes?
If you use this assumption, and so this definition for the entropy current, and you impose that locally you have the fact that the divergence of this entropy current must, the for divergence of this entropy current must increase.
Mm-hmm.
You get realistic Navier-Stokes, but without second order corrections. Because the
no, you get it. This will be the next chapter. The next, say, the equation, the mu S mu will be the next topic. So if you, maybe we can you wait? Yeah. Okay, so can I then, so this was, okay, I have been, in a sense, I have been not really completely honest. I will tell you why then. I don't know if I will, but I don't know if I will have time today, maybe next time, because there are some subtleties involved in this definition, okay? And although this is the, I would say, the most, say, solid form, in a sense, the most, say, conceptually well-founded, but there are some subtleties involved because there is some degree of arbitrariness also in the definition of entropy current, even in this case, which are related to the fact that this hypersurface that I have chosen is arbitrary, okay? So there is a subsection of this topic involving the proof that S mu is an objective definition. So the definition of a field and not just of something which depends on a foliation, okay? But this will, let me postpone this to the, I think at this stage, next lecture, because now my main goal is to show what was mentioned by Andrea Beraudo, so how to obtain the equation of the increase of entropy. So the next step is to find out what is the mu S mu, okay? And to do this, well, I need to introduce some very quickly and very, I would say, informally, concept of differential geometry. Namely, what I need to do is to calculate the change of an integral when the hypersurface changes a little. So suppose you have a hypersurface, sigma, and suppose that I have a small change of this hypersurface to a sigma prime, okay? And I want to know what is the difference between, for instance, d sigma mu phi mu calculated over sigma prime minus d sigma mu phi mu calculated over sigma, okay? To do this, you need a theory, or you need to resort to differential geometry, because this problem can be coped with in a general relativistic framework, okay? First of all, you need to specify what is the concept behind the change of hypersurface. The concept behind the change of hypersurface, even if it is a little one, is a so-called diffeomorphism. So a map which takes any point x to an x prime over this hypersurface on x prime, which is a new point in the space and time. the concept between, so what emerges in this, in parameterizing these changes is the fact that you need a vector field, psi, to define such a change of hypersurface. What is psi? Psi is, in other words, is, say, loosely speaking, is the direction in which this hypersurface is modified, okay? So in other words, you push your hypersurface at each point over some direction psi, okay? The parameter epsilon, or the parameter which describes how far along this vector field I move my hypersurface from sigma to sigma prime is called the parameter of, technically speaking, is the parameter of it's a one parameter group of diffeomorphism. And if it is small, you can call it epsilon, okay? So, in other words, so to summarize, I have a hypersurface, I try to deform this hypersurface to modify it into a new one, and to do this, I need a vector field psi, which specifies the direction, and I need a parameter, which tells me how far I'm going from the initial to the final hypersurface. Then what I want to calculate is this derivative. So this will depend on psi and epsilon, and I want to take the limit of, for epsilon going to 0 of this difference, okay? Since I was talking about diffeomorphism, maybe some of you know that this derivative corresponds to taking a Lie derivative. Okay, this is a Lie derivative along the vector field psi after all. Okay, but I want to emphasize that this is so this corresponds, in other words, to a Lie derivative of this field. Okay, but I want to instead to emphasize the fact that you can see this as a change of the hypersurface of integration. Okay. Now, what does this derivative become? Well, there is a general formula for this. Okay, so you can then make your Lie derivative, use differential geometry, differential forms, which define the integration, and you can make, you can make it very long, but eventually what you get is the following formula: 1/2 an integral over the boundary, which is a 2D surface, psi mu up phi nu, plus an integral over the hypersurface itself of psi mu divergence of phi. Okay? This is a fully covariant formula, can be extended to general relativity, and it tells you that this derivative, so if you change a little this hypersurface of integration, then this derivative gives rise to two terms, one involving the divergence of the field, multiply when you integrate psi mu, multiplied by mu, and then you have this term, which is a boundary. Okay? Now assume that the boundary term is 0, so that this extends far enough in order for phi to be 0, then you are left with a formula where only the divergence of phi is involved. Okay? Now the question is, let us do the same, but let us do the same, if I find it. Yes, so let us do the same here. This I need, maybe I can use this board. Let us do the same, but using the original definition of d sigma mu phi mu. So we have seen that this is just logarithm of z, right? Logarithm of z is d sigma mu phi mu. So if I take logarithm of z with some psi epsilon minus logarithm of z divided by epsilon. This is just 1 over z, and then I have z psi epsilon minus z epsilon, okay? And I have to take limit epsilon 0. Okay, what is z psi epsilon? Z psi epsilon is the trace of the exponent of minus the sigma mu integrated over this modified hypersurface T mu nu beta nu minus Z j mu. Okay? So what I have to do is that I have to take the trace of the difference of two exponents. Particularly, so Z minus original Z is this one, minus exponent of e to the minus d sigma mu, blah, 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 okay? So this is what I have to do. Now, this can be done, okay? It can be done because what you can do is that you can expand. This is a case where you have, in a sense, this reduces to a derivative of a trace. Therefore, it is, can be worked out usually as a normal derivative. And what you get, okay, there are some steps involved, but it's not difficult to work out. What you get is the following, is that when you have, remember that then you have to take this. Okay, what you get eventually is the following, is that this is equal to minus d sigma mu psi mu, okay, times T mu nu mean value local equilibrium beta nu minus zeta mean value of J mu local equilibrium. So let me just tell you how to do this. You have to expand this, how to get that. I mean, you have to take this formula here, okay, and expand this in at the first order by using this approximation at the first order. Then you are left with something in epsilon, which is small. So you have an exponent of epsilon, then you can take as the identity plus epsilon, and then eventually you are led to this formula here, okay? But I will leave you some notes about it.
I think this is correct in that last expression.
What?
I think this is correct in that last expression.
This is?
The indices.
Oh, the indices. Oh, you are correct. Yes, you are. Sorry, I mixed it up. This is nabla mu beta nu, and then you have minus nabla mu zeta. Yes, thank you. Yeah. Right. No, now it's fine. Yeah. No, I didn't copy from the notes. Yeah. What's the reason why you have this? The reason is the following, is that when you use expansion, then you have a divergence of the field here. The divergence of the field is divergence of T mu nu beta nu. The divergence of T mu nu is equal to 0, and then you have T mu nu nabla mu beta nu. Okay? So we have obtained that delta log, let me call it like this, is equal to minus the sigma psi T mu nu local equilibrium nabla mu beta nu minus nabla mu zeta J mu local equilibrium. Okay? And therefore, we can compare with this, and this is equal to d sigma mu psi mu divergence of phi. And you can see this, that if you are at global equilibrium, for instance, this is a special case, you can check this formula. If you are at global equilibrium, This is 0 because nabla mu beta nu becomes a Killing vector. This is 0 as well because this is a constant. Therefore, there is independence of logarithm of z onto the hypersurface, which is what you expect. Okay? But this tells you something more because, where we can write this, because after all, this field psi can be chosen at will, so it's arbitrary. So I can modify the shape of the hypersurface in several directions, or several, with any vector field I like.
There's restrictions on that.
Right? What?
I mean, there must be restrictions on the vector field.
Yes, there must be restrictions on the vector field in the sense that I should obtain some hypersurface which is continuous, differentiable, and then perhaps.
Also, it's inverse of
Yes.
how to make this assumption, to make sure that this will be valid.
Sorry?
How one can make sure that this will be valid for the visit derivation? Like this psi, how to make sure that this psi and its inverse are differential in order to do all of this, right?
Oh, well, I mean, that is, that you can assume this at the beginning. Of course, that is one of the mathematical assumptions you can make at the beginning, that the field size must be, of course, infinitely differentiable, so you have a continuous deformation which is regular, no singular points, and so on and so forth. But this was not the point. The point is that any of such field leads to these two formulae, okay? And therefore, by comparison, since psi is arbitrary, and sigma as well, what happens is that divergence of phi must be equal to minus T mu nu local equilibrium nabla mu beta nu minus, sorry, there is a, well, this was like this, then is plus nabla mu zeta J mu local equilibrium. Okay? So we have a formula for the divergence of phi, which is obtained just by comparing the two definitions of the logarithm of the partition function. On one hand, this is the integral of some, we have shown that this is the integral of some thermodynamic potential current, and on the other hand, we have used the definition of the partition function as the trace of an operator, okay? And we have finally achieved this formula, which is very important because once it is coupled to the definition of the entropy current, now we have, let me use this nabla, nabla mu as mu is equal to nabla mu, and then we have seen that this is phi mu plus T mu nu beta nu minus zeta J mu. Okay, let's take the divergence of this expression. And then we have divergence of phi plus, okay, nabla mu T mu nu is 0. This is the actual stress energy tensor, okay? Then we have plus T mu nu nabla mu beta nu. Now, second term, okay, this is conserved, therefore divergence is 0, then we are just left with nabla mu zeta J mu. Now we plug this formula in there, and what we get is the following. And this is really one of the most important formulae of this course. That is not my finding. This is a formula which, for some reason, was not that popular. Or maybe it was found by Wirth in the early 80s or late 70s. Here it is. The divergence of the entropy current, this must be framed, is given by the difference of the stress energy tensor, of the actual stress energy tensor, its value local equilibrium, nabla mu, beta nu, minus J, a similar term for the current. And this is very important because it tells you what generates dissipation. So what generates the increase of entropy. What generates increase of entropy is the difference between the stress energy tensor, the actual value, and the value of local equilibrium. It is precisely the term that I have denoted with delta T mu nu, nabla mu beta nu, and then we have another corresponding term, which is delta J mu, which I have defined in words that diffusion currents, okay? Whenever T mu nu is equal to the local equilibrium value, no dissipation. So this, in a sense, contains, as a special case, a proof that in the ideal hydro, where you assume that T mu nu is equal to T mu nu local equilibrium, and especially, well, T mu nu local equilibrium is usually meant as the ideal form, but not necessarily, okay? So even if it has some gradients, some terms which include gradients, but still, that is non-dissipative. So if T mu nu is equal to mu nu local equilibrium, no dissipation. The same should happen for the current, okay? So I think this is a very important formula, which was obtained in the late 70s by Christian van Wert in a not so popular paper, but I think very important, although the derivation was different, was made in a different way, but still, this equation shows a very important point, because in quantum relativistic approach, it tells you really what should be meant as dissipative and non-dissipative, okay? There are some questions to be clarified, some issues. I leave some of them to your reflection, hoping that you are interested in this topic. And if questions, I hope that questions will arise over these 2 days before my last lecture, but otherwise, on the last lecture, I will address some of them, okay? Especially the dependence of these results onto the foliation, so the hypersurface which is chosen, okay? Okay, I think I'm done for today. And so are there some final comments or?
The positivity of the versions of entropy current, does it impose some constraints on the coefficients in this delta T mu?
Yeah, yes, of course, yes. So if you impose that this must be larger than 0, then this is, of course, the same as the classical approach. Then you have that this term should be positive. Therefore, this implies that all the terms in delta T mu nu, if you expand this to first order, second order, they should be positive, yes.
I see how you impose constraint in the second order, just something proportional to number of mu plus nu, for example. But then if you go beyond that to other gradients, is there a way to make sure that they are positive?
I don't know. I think, I don't know. The question is simply very simple. Since I have not really, I don't know of any, say, let me see, I don't know of any, except that those obtained by, writing down all possible, say, terms in a grand expansion. I don't know of any systematic study of, say, within this framework. So I can't tell you this for the present, and but eventually, that of course that it should be the case, so that you cannot. So in other words, what you have to so the positivity of the entropy production means that under any circumstance, so under any field, okay, this is to be positive. Now the question is, if you can say, in a word, if you can isolate, okay, so if you can single out a term of a higher order such that all the previous, say, terms are 0. I don't know if this is possible, because this requires, some assumption on the shape of this beta function, and then, it's an interesting point, but which Maybe it is worth being explored in more detail, so I don't know. Yeah. Because I don't know if you, for instance, if you take, for instance, nabla mu beta nu, so I can assume that the gradient is 0, but then of course you have a constraint on the shape of the function, those are at the higher orders, right? Yeah. Yeah. And then, well, I don't know. That's a very interesting point. Yes, please.
Maybe something related also to metric conditions, because I was wondering that these gradient corrections to the local equilibrium may lead to violations of the metric conditions. For example, you may impose that because they are constraints on delta T mu, right? And then
What, it depends on what you mean by matching condition.
So the
yeah.
matching conditions, from what I understood in this framework, the matching conditions, they are the delta, for example, they are constraints on the delta T mu, right? And then
Yeah, you may write this as this way, yeah. For instance, yeah.
but you have also gradient corrections to the local equilibrium.
Right. Yes.
So you may have, for example, an energy.
This is equivalent to this
You
thing.
can have for example, a heat flux.
Yes.
Just because of quantum corrections.
Oh, you may. Well.
If you don't know which conditions, it is a definition that you don't have a heat flux.
In principle, you may. No. Depends on what you mean by heat flux.
The heat flux is doing that the projection of the irreducible decomposition of the energy moment intensity will be the vector part of the energy moment intensity.
Okay, if you this okay in this okay this approach this is, okay this approach I mean this is not I mean this is not heat flux. For instance, that if you calculate that if you calculate T mu nu at global equilibrium, okay, in a rotating fluid, if I remember correctly, then there is something which is proportional to you have a term Q mu beta nu, I guess. You have a term which is that you would interpret as a heat flux in the usual decomposition, which is simply there. So it's
Isn't there related to the asymmetric, the antisymmetric part of the energy moment intensity?
okay. Then maybe Andrea, do you remember all of the terms that? Do you remember all of the terms that we calculated at global equilibrium? Maybe we have to look together. Anyway, so what I mean is the following. In principle, you may have even if it is global equilibrium, okay? You may have something like this. Let me call it, well, I don't know, say T mu u nu plus, okay, plus T mu u nu. Okay? You may have something like this, with this term depending on omega, okay? For instance, maybe, well, omega alpha, beta alpha, or something like this. So you may have something like, no, in this case would be 0. But you remember, maybe you have an epsilon. Oh, yeah, that is epsilon mu alpha beta gamma, and then we have omega alpha beta. Yeah, I don't remember. Anyway, I have to look at the formula because I don't remember by heart. Anyway, but what I stress that in principle, even at global equilibrium, we have a term like this. But you would not call it this heat flux, because heat flux is something which is meant to be dissipative. Okay. So this is just a longitudinal term, which is you can interpret this as a change of frame in a sense. So we are not in the Landau frame, okay? We choose U like this, okay? In this case, beta is a Killing vector. And when you are at global equilibrium, you find out that you have many more terms than expected. So not just the ideal form, but lots of other terms which would be interpreted in the traditional approach as dissipative, but they are not indeed, okay? Because this is T mu nu at global equilibrium, so there is no dissipation, in fact. Okay? But, in order to answer your question in a more detailed form, I will have to go to the form that was calculated, and I don't remember, there are many terms at global equilibrium, including vorticity, acceleration, and then you will see that it's not just the absence of, it's just that the absence of this term which defines global equilibrium, but it is the fact that the deep, say definition of global equilibrium when you have a time-like killing vector. That is really the most proper definition, and I would say that, which is also, far more suitable for general curved spacetimes, because, in general spacetime you do not have, for instance, isotropy or translation symmetry. You may have different symmetries, but still you have equilibrium if you have a global time-like vector. And this does not mean that T mu nu has no terms proportional to T mu nu like this. So it may have such terms, and they do not imply dissipation. So now it's a question of semantics. That, do I want to call this heat flux? Well, it depends. If by heat flux you mean just because of this special form, okay, you can keep it calling heat flux if you wish, but to me, heat flux sounds more like, you have a dissipation. Therefore, I would not call it like this, yeah. This is just my taste.
I think we should stop here, otherwise we will go
Yeah.